In this video, I'll talk about the Cartan-Thullen theorem. So the Cartan-Thullen theorem says that an open subset of C to the n is a domain of holomorphy if and only if it is holomorphically convex. So if you just wandered here from the internet and you want to know what a domain of holomorphy is and what is holomorphic convexity, go ahead and take a look at my previous video where I'll talk about this in detail. So this video will be exclusively about the argument of this theorem. So to begin, let us assume that omega is holomorphically convex. So assume that omega is holomorphically convex. Okay, so we'll return to this condition in a minute, but first, let's take a compact exhaustion of omega. So let Kj be a compact exhaustion of omega. So what does this mean? So this means that obviously each Kj is compact. Each Kj is contained in the next Kj, so in Kj plus 1. And then exhaustive means that for all K compact subsets of omega, there exists a J such that K is contained in interior of Kj. Okay, so since omega is holomorphically convex, one can take the Kj's to be equal to their analytic hull. So why is this? Well, we can replace Kj analytic hull. Okay, so since you're holomorphically convex, then the new exhaustion will also be a compact exhaustion, right? So obviously, Kj will always be contained in Kj plus 1 hat. Due to holomorphic convexity, as I said, Kj hats are always compact, and then also this condition will always hold. Okay, so now pick a z on the boundary of omega and a sequence zj such that each element zj is in Kj but not Kj minus 1, and most importantly the zj's converge to z on the boundary. So the picture somehow is like this, right? So this is omega, this is z, and the zj's sort of converge to the z on the boundary. Okay, and we somehow make this condition, which is always possible since the Kj's are given exhaustion. Okay, so claim the following. So we claim that there exists an F in curly omega, so F holomorphic, such that the limit of F in absolute value when taken at the zj's is actually plus infinity. So, like, assuming the claim for a minute, this would imply that F is obviously not extendable here, C. And then this would imply that omega is a okay, which is what we want. So let's argue the claim. So let's go proof. So how do we go about that? So F will be constructed as a sum of an absolute convergence sum of holomorphic functions. So let's construct this sequence that will eventually sum up. So we'll do that inductively. So just take F0 to be identically 0. And let's assume now that F1 and Fk minus 1 holomorphic functions are already constructed. Okay. So since zk is in kj, but not kj minus 1, let's not forget the hats, we know that there exists a gk holomorphic in omega such that the absolute value of gk and supremum taken over kj minus 1 is less than 1, but the absolute value of gk zk is greater than 1. So this just follows from the fact that kj hat is the same as kj hat. Okay, so now we will define fk to be a really big power of gk. So take such a high power here so that so for make this precise, so for n big enough, we get that. So fk, supremum of fk on kj minus 1 is less than 1 over, let's say, 2 to the k. So 2 to the, okay, so I messed up some indices here. So zk is in kk hat minus kk minus 1. Okay. So k and j are obviously the same here. Sorry about that. So for big enough n, we have that supremum of fk on kk minus 1 is less than 1 over 2 to the k. And again, for big enough n, due to this condition, we can assume that gk zk in absolute value is greater than, let's say, k minus, or really plus, the sum of, sorry, not gk, but fk. We don't care about gk. So fk is greater than sum of j from 0 to k minus 1 of fj zk. So this is a known quantity. This is a fixed quantity. This is already constructed in the previous steps. So we just take n high enough here so that this bound is satisfied and also this bound is satisfied. This is possible to do. Okay, so now we claim that we can just simply, so we can just simply take f to be the sum of and then this will be holomorphic. Okay. What's going on? Well, what we know is so on each kj, so we know that the fj's, so let's say on a kj0, the fj's are less than 2 to the j for j greater than j0, right? So this implies, due to the exhaustiveness here, that this condition, the sum being holomorphic, is satisfied because the sum is absolutely convergent on each compact subset of omega. Okay, so the next thing that will be interesting for us is the value of f at a fixed zk. So it's easy to see that this is greater than the value of fk at zk in absolute value, minus the sum from 0 to k minus 1 of fj zk, minus the sum from j going from k plus 1 to infinity fj zk. So what's going on? Due to this condition here, we get that this part is greater than k. So then we're left with this last sum. But we know that each of these zk's are will land in k j minus 1. So from this condition, we know that this is greater than what? K minus sum of 1 over 2 to the j. J greater than k minus 1. And then all in all, it's kind of a crude estimate, but it's perfectly fine to say that this is greater than k minus 1. So what do we get? We get what we wanted. We get that the limit of fzk is plus infinity in absolute value. Okay, and this is what the claim wanted to argue. So we are done with the claim. And then as we saw here up top, the claim implies that f is not extendable near z. So omega is the domain of holomorphy. Okay, so now this implies one direction of Cartan-Thullen theorem. So let's go the other direction. So let's assume that omega is a domain holomorphy. And then we want to argue that this implies that omega is holomorphically convex. So for that, let us take K, a compact subset of omega. And let's introduce the sup distance of K to the boundary. So well, there's many ways to approach this. So what I will do is I'll just take the unit polydisk. So n copies of the disk. And I will just introduce this notion, let's call it delta K boundary of omega. This will be the supremum of positive R such that K plus R D, K plus RP is a subset in omega. So it's not hard to see that this is actually, as I said, the L infinity distance of K to the boundary of omega. Now, to proceed, so pick a fixed epsilon. That's possible. So what did we get from here? Also, let me call this delta just simply by delta. So we know that, what do we know from here? So we know that if I pick an A in K, everything including omega, then A plus 1 minus epsilon delta P closure. So this polydisk, so this is going to be the polydisk centered at A with radius 1 minus epsilon delta. This is going to be compactly inside omega. So in particular, one can take a power series expansion. So can take power series expansion of any F holomorphic in omega at A, and with this on this polydisk. So then there, about the coefficients, the Cauchy inequality will say, so by the Cauchy inequality will imply the following about the coefficients. So it will imply that for every poly-index, multi-index, I, capital I, these partials, the Zi partials at A in absolute value, times 1 minus epsilon delta to the power absolute value I. So this should be less than what? It should be less than supremum on K. So maybe I want to supremum on K plus minus epsilon delta hat of F. So this is just simply coming from the Cauchy inequality, and then you get the Cauchy inequality if you need a reminder from the Cauchy formula, by you differentiate the Cauchy formula and you just take an absolute value, go inside the integral, and that's what you get in one variable. In the multivariable case, you do the exact same thing, and then this is what you get. Now, here's the cool thing. So this correspondence, A to partial of F at A, this is holomorphic. And we have this bound for all A in K. So if you have a uniform bound for a holomorphic function, for the absolute value of holomorphic function on K, it automatically extends to K hat. So we get that, let's call this inequality star. So inequality star actually holds, so holds for all K hat. But then by Abel criteria, we get something interesting. So let's pick now an A in K hat. So K hat is inside omega. It's not clear if it lies compactly inside omega. We will argue that. Now at A, we can develop F into power series. So we get that Fz is equal to sum of and then this holds near A in some polydisk neighborhood of A. However, by the Abel criteria, we get that since this estimate holds, so by Abel criteria, convergence of power series and star, we get that what? We get that the right-hand side converges on A plus 1 minus epsilon delta P. So we get that on the right-hand side, this is, so the right-hand side is holomorphic on A plus 1 minus epsilon rho P. But also the right-hand side near A is the same as F. So then we automatically get that since omega is a domain of holomorphy, we get that this whole thing, this whole polydisk needs to be contained in omega, because if it wouldn't, then this power series would extend F locally. So since it's the domain of holomorphy, we get that A plus 1 minus epsilon delta P needs to be contained in A for all A in K hat. Okay, but then we're almost done, because this implies that K hat plus 1 minus epsilon delta P is inside omega for all epsilon in 0, 1. But then, by definition, this implies that delta K hat boundary of omega is at least delta, which was delta K boundary of omega. Obviously, K is always less than K hat, so the reverse inequality is trivial. So we actually get that these two are equal. But this is positive, so that means this is positive as well. So this implies that K hat is compact inside omega, and omega is holomorphically convex. Okay, thank you very much for your attention. So this gives the proof of the Cartan-Thullen theorem. If you have any questions about the argument, if there's something isn't clear, you spot some typos, I'm sure there's many, make sure you mention them in the comments. Thank you very much.